When we look at an atom, we find three key particles inside it: protons, neutrons, and electrons. A typical atom is electrically neutral, which means it has an equal number of protons and electrons. Protons carry a positive charge, electrons carry a negative charge, and neutrons have no charge at all. Now, you might wonder, why do neutrons even exist? Here's why. Since protons are all positively charged and like charges repel each other, they would naturally push away from one another inside the nucleus. Neutrons act as a stabilizing force, holding the nucleus together by reducing that repulsion. Since atoms are far too small to see with the naked eye, when we take a pure collection of one type of atom, we call that substance an element. For example, a piece of gold is made up of billions upon billions of gold atoms. Every element has its own unique atomic structure. Today, we know of 118 different types of atoms or elements in existence. According to science, the universe began with the Big Bang, a massive cosmic explosion, approximately 13.8 billion years ago, which gave birth to our entire universe. In those early moments, mostly hydrogen and helium were formed, along with trace amounts of lithium. All the heavier elements, from carbon and oxygen all the way up to uranium, were forged inside stars and during supernova explosions. Elements heavier than uranium are primarily created artificially in laboratories. So what makes one element different from another? The answer is simple. The number of protons in the nucleus. This number is called the atomic number, and it is the true identity of an element. For example, every carbon atom has 6 protons. Every gold atom has 79 protons. If you were to remove a proton from gold, it would no longer be gold. It would become platinum, which has 78 protons. Add a proton to carbon, and it becomes nitrogen, which has 7 protons. The proton count defines everything. Now, just as we can remove protons, we can also remove or add electrons and neutrons from an atom. Take carbon-12, the most stable form of carbon, which has 6 protons, 6 neutrons, and 6 electrons. If we remove or add an electron, it becomes an ion. An atom that loses an electron is called a cation, that is C+. An atom that gains an electron is called an anion, that is C-. Similarly, if we add or remove a neutron, it becomes an isotope. Carbon-12 has 6 protons, 6 neutrons, mass number 12. Carbon-13 has 6 protons, 7 neutrons, mass number 13. Carbon-14 has 6 protons, 8 neutrons, mass number 14. Here, 12, 13, and 14 are the mass numbers, which is simply the total of protons, neutrons. This is the key difference. Atomic number is the number of protons only, which is the element's real identity, and mass number is the number of protons plus neutrons combined. Now let's discuss electron shells, valence shells, and valence electrons, as these concepts are essential to understanding the periodic table. Electrons don't just float randomly around the nucleus, they orbit in specific energy levels called shells, which are labeled K, L, M, N, and so on. Each shell has a maximum electron capacity. The first shell, K, can hold up to 2 electrons. The second shell, L, can hold up to 8 electrons. The third shell, M, can hold up to 18 electrons, and this pattern continues. In reality, electrons fill shells based on energy levels rather than capacity alone. For example, potassium, atomic number 19, has an electron configuration of 2, 8, 8, 1 instead of 2, 8, 9, even though the third shell can hold up to 18 electrons. This occurs because the lowest energy sublevel of the fourth shell is actually lower in energy than the remaining sublevels of the third shell, causing the electron to fill it first. Moving on, the valence shell is the outermost shell of an atom. The electrons within this shell are called valence electrons, and they are the ones responsible for participating in chemical reactions. The periodic table organizes all 118 elements in a very specific way: 7 horizontal rows called periods, 18 vertical columns called groups. As you move left to right across a period, the valence shell stays the same, but the number of valence electrons increases. As you move top to bottom down a group, the number of valence electrons stays the same, but a new shell is added each time. These repeating patterns across the table are called periodicity, and they allow us to predict how elements will behave chemically. We'll dive deeper into periodicity and the elements of the periodic table in a future video. Now, let's zoom in even further, beyond protons and neutrons, to the smallest known particles in existence, quarks. If you zoom into the nucleus of an atom, you'll find that protons and neutrons are themselves made up of even smaller particles called quarks. According to modern science, quarks are the most fundamental building blocks we know of. There is nothing smaller. There are 6 types of quarks, known as flavors: up, down, charm, strange, top, and bottom. However, all ordinary matter around us is made primarily from just 2 of these, the up quark and the down quark. A proton consists of 2 up quarks and 1 down quark. A neutron consists of 1 up quark and 2 down quarks. Now, here's where the math gets beautiful. An up quark has a positive charge of 2/3, while a down quark has a negative charge of 1/3. Proton is formed by 2 up quarks and 1 down quark. 2/3 plus 2/3 minus 1/3 is +1, a positive charge. Neutron is formed by 1 up quark and 2 down quarks. 2/3 minus 1/3 minus 1/3 is 0, a neutral charge. This means that everything you see around you, the stars, planets, water, rocks, trees, and even you yourself, is ultimately built from these incredibly tiny, invisible quarks. If you enjoyed this video, make sure to like and subscribe. See you in the next one, where we will talk about how every element in the periodic table formed after the Big Bang.